Swayam Prabha. Digital India. Educated India.
Hello everybody. So, welcome to my next lecture, that is the structure and geometry of carbenes. Okay. So, in the first class we have learned about the introductions of the carbenes, or rather reactive intermediates, where we have learned that what is reactive intermediates, what are in general their characteristics, and how carbenes as a reactive intermediate behaves, and what are their special characteristics among all reactive intermediates. From there we have classified that carbenes are two types, one is singlet, another one is triplet. So, singlet, another one is triplet. Okay. So, now we will learn their structure and geometry. So, today in this lecture we will learn structure and geometry of carbenes. Already we have started that one, these particular things little bit in the last course, we will continue that. So, in case of carbenes, as we have already showed you, still I would like to draw the same thing here for better understanding. Okay. So, let us make different color. Okay. Or here, sorry, okay. So, we can give okay. So, now we will fill up the orbitals. Okay. So, this is called singlet, okay, and here this is the sp2 and this one is the p orbital. Similar here. Okay. So, this is called triplet carbene. Okay. This is sigma 1, p pi 1, you can call it, because both these electrons they are occupying two different orbitals, and here they are occupying in a single orbital. Okay. Here they are paired up, that is why they are called singlet, and if you go through the multiplicity calculation, actually that is why their name is singlet and triplet. Okay. So, in case of singlet, this is the both of them has been paired up, and in case of triplet, these are actually both are unpaired electrons and they are in two different orbitals. So, if you calculate the multiplicity, then as per that their name comes like singlet and triplet. Okay. And it has been found their structures are bent. So, they are in general bent carbenes. Okay. Theoretically or experimentally it has been proved that they are bent in nature. Now, is there any linear carbenes? Though they are rarely found or they are in general most carbenes are not linear, most carbenes are not linear, but still we can, if it happens, how it looks like. Okay. So, in this case we can actually put up these two electrons, you can draw in this way. Okay. In this case we can draw, they are orthogonally situated. So, okay. So, like this way. So, here this is also p orbital, this is the p orbital, okay. These are the pure p orbital, this is also p orbital, okay. And here this is linear and this is the sp hybridized carbon atom. Okay. So, now these two electrons are totally occupying the pure p orbitals, they do not have any s character. Okay. So, these unpaired electrons here the unpaired electrons, okay, have no s character. Okay. So, this is called linear carbene. Okay. So, what we have learned that there are bent carbene as well as linear carbene, even though this is not very much existence, this is not having so much of existence, but still this is the linear carbenes structure and it looks like this. And if you see, this is also triplet and can write it like this, p pi 1 p pi 1. Okay. So, what we have learned that the electronic configurations of these carbenes are having like this. In some case, if it is a bent carbene, they also have singlet as well as triplet, and in case of linear carbene, they have this type of triplet carbenes. Okay. So, next if we see this bent triplet and singlet carbenes, these bent carbenes in general, as I said that most of these carbenes are bent, and that also experimentally and theoretically it has been proved. So, what are their structures and how these bond angles behave? Okay. See, they are bent, that means these particular carbenes, let us say we can write like hydrogen here, okay, and this is having one sp2 orbital, one p orbital. Okay. So, next we can fill it up like this. Okay. Now, we can give the electrons. So, this is for triplet. Okay. So, this is for triplet carbene. So, we have already drawn this. Now, we will draw again the singlet one. Okay. Okay. So, this is the two things. Now, for singlet carbenes, it will be like this. Okay. Now, even though they are bent, what will be there? These bond angles. That means, we calculate this and this. The bond angles, it has been found for triplet carbenes, the bond angles are larger. So, these have larger bond angle and this is having smaller bond angle. Larger bond angle means this is having around 130 to 150 degree and here it is having 100 to 110 degree. Okay. So, triplet carbenes are having larger bond angle and the singlet carbenes are having smaller bond angle. Now, question is that why it is like this? Okay. Why the bond angles varies for triplet and singlet? Now, if we see that here for this particular singlet carbenes, they are in this sp2, here it is sp2 and this is the, as you have seen, sp2 and this is the p, here also same, this is sp2 and this is p. We have seen this. So, now definitely these number of electrons are actually creating this difference. So, if you see here for singlet there are one pair of electrons, okay, they have paired up. Now, and in this case here there are only one electrons in this sp2 and another one electron is in p. Now, if we see in this case the repulsion between these two, here only one electron, okay, and here there are two electrons. Definitely here it will be more repulsion than triplet case. So, for singlet case the repulsions will be higher than the triplet case and if this repulsions is higher then automatically here the bond angle will decrease. Okay. So, in case of singlet that means if it is 2 electrons it is having more repulsion, okay. And whereas here it is only one electron. So, this is having less repulsion. and if it is less repulsion, that means this bond angle here, these bond angles, this will be larger, that is here 130 to 150 degree, and if it is this repulsion is higher, then this will have the smaller bond angle. So, this will have 100 to 110 degree. One interesting point is here that triplet carbenes are actually experimentally you can prove. How? There is one particular technique. If we do experiments, always we have to go through certain experimental procedures to identify whether our products or intermediates that has formed or not, right. So, we have done some reactions, let us say as per example, and something we have reacted, we got some products, but how we are identifying them, okay? Because after isolations of that particular reactions product, we do not know whether they have formed or not. So, we have to take help of certain analytical techniques, as per example NMR, that is nuclear magnetic resonance spectroscopy, or mass spectroscopy, like there are similar that kind of spectroscopic methods are available to determine the structure of the compound. Here also for this particular triplet carbenes, it can be observable by ESR. Okay. So, triplet carbenes, okay. So, triplet carbenes, they are actually observable by ESR, okay. Electron spin resonance spectroscopy, okay. So, ESR. So, this is called ESR spectroscopy or electron spin resonance spectroscopy, where if there is any unpaired electrons are available in the intermediate, you can actually identify them through this particular technique. Okay. But in case of singlet, as it is paired up, so it will not be visible or it will not be characterized by this particular technique. So, in this way you can actually determine which one is triplet and which one is singlet by this spectroscopy. Okay. So, even though these bent carbenes are there like triplet or singlet, they have different bond angles. We have learned that why these bond angles are differ. Okay. So, it depends on their number of electrons, how they are actually occupying the corresponding orbitals. Okay. Next, we will learn the electronic structure of these bent singlet and triplet carbene. So, next what we will learn? We will learn the electronic structure of bent singlet and triplet carbene. Okay. So, first we will draw this bent singlet carbene, that is I am just drawing like this way. Okay. And so, if we draw their first, they have these bonding orbitals. Okay. Next, like this one and this non-bonding. So, we can write in general there are these two sigma bonds they are this, then one non bonding sp2 orbital and one p orbital here, okay, empty p orbitals, and in one case there is this anti bonding sigma star. Just a minute here, yeah, we have to draw like this. Okay. Okay. So, now if we filled up the electrons, as we know or we have already learned that there are total 6 valence electrons. So, we can fill up like this. Okay. So, this is the bent singlet carbenes. That means, here this p orbital, this is the sp2, here the p orbitals, we have already learned this. Now, if we see its molecular orbitals, actually here it is like this. So, here these sp2 orbitals, that is actually having these 2 electrons and they are all paired up. Similarly, if we now go for bent triplet carbene, okay. So, like this. Okay. Okay. So, here also this is sp2, this is the p orbital. Unlike the singlet carbene, here both these orbitals are actually filled up with 1 electrons. Okay. So, now again we will do this similar way. Okay. So, now again we can write like this sigma, let us say this is sp2, this is p, this is sigma star. So, if we start filling up this one electrons here, these are the all these bondings, and then this sp2 orbitals, that is filled up with 1 electron, and p orbital, that is also filled up with 1 electron. So, this is the bent triplet carbenes, and their these orbitals are filled up in this way. So, these are their electronic structures, and here actually these things guided that how they will behave. Okay. Next, these are for the bent singlet and triplet carbene. Now, if we see for linear triplet carbene, how does it look like? So, as per example like this. So, this is the linear triplet carbene. Okay. So, it will be like this as per example. So, C hydrogen, and there will be 2 orthogonal p orbitals. Okay. Okay. So, this is the linear triplet carbene, this is the sp hybridized, these are the p orbitals. And this is the sp hybridized carbon atom. Okay. Now, if we again draw its like that way, here these 2 p orbitals, they are similar in energy and then sigma star. So, 2 bonding, then 2 p orbitals. Okay. Now, let us we fill it up. So, total 6. Now, they will stay like this, because these 2 p orbitals are same in energy, okay? And as they are same in energy, so these 2 electrons will occupy both of these 2 p orbitals. Okay. So, here we can, these are the 2 orthogonal p orbitals occupied with two electrons. Okay. And these two electrons remain unpaired, 2 electrons will remain unpaired because of the due to electronic repulsion. Okay. So, these kind of linear triplet carbenes, rather as these 2 electrons they will remain unpaired. So, they can actually act like a di-radical. Okay. So, what we have learned? We have learned the electronic structure of band as well as linear triplet carbenes. Okay. Thank you very much.